Hello, this is Ms. DB. In this video we are going to look at systems of linear inequalities. So previously you've been working with systems of equations, which are lines that either cross at one point, or we saw that sometimes they never cross, or sometimes they're the same line. Now we're going to look at inequalities, and we're going to graph two inequalities at the same time. And remember from last quarter that when you graph an inequality, you shade either above or below, depending on if you have greater than or less than. So we're really going to be looking at where does the shading overlap in our system of inequalities. So you're definitely going to want to have Desmos or GeoGebra or Sketchpad open. Some of these you will have to share your graphs, so you will want to pick something that you can take screenshots of or add links to. So this example here, it shows to graph y is less than or equal to negative 2x plus 4 and y is greater than x minus 3. So what we do is we graph the boundary lines. You could type y equals and then shade on your own, but since we do have technology, let's go ahead and use it. So in Desmos, there's a keyboard down below that has the less than or equal and the greater than or equal symbols. You're going to need those. So we want y is less than or equal to negative 2x plus 4. And Desmos automatically creates the right kind of boundary line. In this case, it's a solid line because it's less than or equal to, and it shades in the correct spot. In this case, it's below. And then on the same graph with the same one in view, don't turn this off by going like that. We want to see it. You're going to graph the other one at the same time. Y is greater than x minus 3 for this problem. And you can see that it did a dashed line for greater than, and it shaded above the line. What we're really interested in here is where does the shading overlap? So the first one shaded below this line. The second one shaded above this line. And if you look at both of them at the same time, this kind of darkish red region, that's the solution to this system. So the solution is not a number, it's not a coordinate, it's a graph that shows shading, dark shading, where the two different shadings would overlap. So in this example, they put this image, it looks a little different because it's different colors, but the only difference is that they had blue and we had gray. You can actually change these colors by clicking on this button here, then click on the point, and then you can pick different colors. You don't have to, but look how close it looks now to this solution, because red and blue make purple. All right, so you're going to do that for several problems on your worksheet. This is just another example so you can look back. To check and make sure you have a solution, you would pick any point from the double shaded region. So in this case, this dark purple, you'd pick any point like 0, 0. And you would try it in both inequalities and make sure that it's a true statement. So 0, 0 is super easy because all the x's and y's become 0. So we'd have 0 is less than or equal to 4. Well, that's true. 0 is less than 4. And then in the second one, we would have 0 is greater than 0 minus 3. 0 is greater than negative 3. Also true. So the point 0, 0 from the double shaded region is a solution. So that's how we check it. All right, sometimes when you graph these, you will get no solution. The shading will never overlap. Let's do a different one where the shading would never overlap. So if the shading never overlaps, we have the same slope. We looked at that before. And then I need to maybe do something like that. So in this one, I shaded below the first line and I shaded above the second line. There is no purple. There's no place where the two shading areas overlap. So this would have no solution. And sometimes the region between the lines is a solution. Let's see if I can show that. In this one, if I just had y is greater than negative 2x for the other one, there is some solution, and it's the place where it's below the blue line and above the red line. So any point within this band would be a solution. All right, so the first few problems you're going to discuss, and there's nothing wrong with graphing these and then deciding the answers. So you can just you have technology at your fingertips, you can just type this in and then use that to help you answer the question. So here's the graph, and it says how many solutions will it have and why. And then you can do the same thing for number 2 and number 3. And it says where will the solutions be, so maybe it'll be between, maybe there'll be a shaded region, you decide. All right, and then on these, all you need to do is use technology to make these graphs 6 through 10, and then attach a link or a screenshot of your graphs here. So I'll just, look at number 9. Let's look at that one because there are 3 inequalities. Let's see what that does. So we have our first one is 5x plus 2y is greater than or equal to -2. The second one is 3x is less than or equal to 15. This is going to be a vertical line. That's okay. And then, because there's no y in it. And then the last one for number 9 is x is greater than or equal to 2. Make sure you're using the correct inequality signs. If you need the underlined version, you have to use the Desmos keyboard. So where is the solution? I have 2 blues, so it's very confusing. So I'm going to change one of these to a different color. Usually Desmos will automatically do different colors, but I had already set this one to be blue, which is why that happened. So now I can see better. I'm going to hide this just for a minute. I'm going to show that the first one that we did, I think was this line right here, and it's shaded above the line. And then I shaded this vertical line, oh, it was right here, this red line, and I shaded less than, and then the green line I shaded greater than. Kind of confusing what's all going on. So there's the blue line I shaded above. Then I added in this one. So the solutions for these 2 would be this triangular region that's kind of purple colored. But then when I add in the x is greater than or equal to 2, it's going to give me a vertical line right here. So the only solution will be in this narrow band and only up to here. These down here are not solutions. So to share your graph, you can either take a screenshot and paste it, or you in Desmos you can get a link to share your graph. So click on, oh, I might have had this a little bit too, I think you can't see the way I have this. Now you can see it. So I made it really big. This button right here lets you share the graph. And it gives you a link, and you can copy that link, and then you can come back to your worksheet, if I can find it, under all of my other things. Here it is. And this was number 9. So I'm going to Control V to paste that, and then this is important, hit the space bar one time to turn that into an active link. What happens now is when I click on this, I can see the exact same graph that you wanted me to see, the one that you just made, this graph. Okay, let's go back to the worksheet. And now I have my graph there. All right, the next thing that we're going to talk about is linear programming. I'm going to resize this so that we can... Okay, so I resized it so we can see both the Desmos and the graphs at the same time. And now we're going to talk about linear programming. That is when you want to find a maximum or a minimum value of a function that satisfies a given set of constraints. So these are mostly real-world problems, like that x has to be positive and that you only have so much of something to use. And we have a feasible region, first of all, that we're going to find with some of these. So the feasible region is what could this possibly include? For example, Jillian is planning a green roof that will cover up to 600 square feet. So a green roof is when you put dirt on top of a roof. It's usually a flat one or slightly slanted, and then they plant things on it. And there's a lot of benefits, but you have to be careful that you don't put too much weight up there. Okay, so she's going to use blue lagoon sedum and raspberry red sedum. Each blue lagoon sedum will cover 1.2 square feet. Each raspberry red sedum will cover 2 square feet. And then it's got some cost in there as well. So the constraint is that neither of the plants, if B is the blue lagoon and R is the raspberry red, neither of those can be negative. Plants are only going to be positive. So the first thing we did is we included those limits on our region, because it wouldn't make sense to include negatives. Second thing we did is an equation about the areas. The blue one takes 1.2 square feet, the red one takes 2, and the most that this roof can be is 600 square feet. So that's less than or equal to 600. And then the second one is the cost. She doesn't want to spend more than $1,000, so then you put the cost of each plant, and that would be less than or equal to 1,000. So then we graph all 4 of these at the same time. When you graph all 4 of these at the same time, that gives you your feasible region. That means that if you pick from the B and the R, the B is the horizontal and the R is the vertical, any point within here would satisfy the constraints. However, picking 50 blue lagoon and 50 red raspberry is not going to give you that area that she wants to get close to. So this is just a way to find the region that your solutions can lie in. And you can do that in Desmos. Now these are B and R, we would have to change it to X and Y, but other than that, you can type all of this into Desmos and get the exact same graph. The shading will overlap to show that exact same region. But usually in linear program, we don't just want the possible region, we want like the maximum amount of plants she could buy in order to cover the whole roof. She doesn't want to just, cover a little area. We want the maximum amount generally. Or sometimes you want the minimum, like the minimum cost. So what we're going to do, again, the one we just looked at was an objective function that could have a maximum and a minimum value. And sometimes it's unbounded, like you can't, in this example here, you couldn't find a minimum. In this example here, you couldn't find a maximum. The ones that you'll do will tell you whether you're going to find a minimum or a maximum, and you'll be able to find it. And we're mostly going to be working with this bounded feasible region that will have all the boundary lines will be defined, and you'll be picking the maximum or the minimum point from within there. So the key is that once you have your feasible region, you are going to look at the vertices. So there's a vertex here at 0, 0. There's one here at 0, 1. There's one here at 4, 3. And there's one down here at 6, 0. A vertex is just a point at which, it's like a corner, at which it starts to change. See these points that are on the edges, the corners of this shape. So the vertices mark that changing place. And then what we're going to do is they'll give you a function to either maximize or minimize, and you will plug the x and y value of each of those coordinates in. So you'll have to do this 4 times because there was 1, 2, 3, 4 vertices, and you'll find either the minimum or the maximum value depending on what they ask you to find. So in this one they wanted to maximize it, so the largest number would be the answer, 4, 3. This point right here would be the maximum of this linear programming problem. So you are going to, for number 12, 13, 14, 15, you are going to first graph the feasible region, and you'll note that 12 matches 14, and then 13 matches 15. So first you'll just make the region, and then you're going to use your graphs from 12 and 13 in order to maximize for 14 and minimize for 15. So we'll do one pair together, and then you'll do the other pair on your own. I have no preference. What do you guys think? Should I do number 12 or number 13? Since you're not here, I'll just pick number 12. So I am going to type in all 4 of those inequalities to get my region. X is greater than or equal to 0. So that just basically puts it on all the positives. And my next one is that y is also greater than or equal to 0. So now I'm only in the first quadrant. The overlapping region is only showing, I want to move this. There. It's only showing that it will be in this first quadrant here. I can make this a little bigger. There. Okay, and then my next one is going to give me a diagonal line. Y is less than or equal to 1.5x plus 1. I really don't like the black color. It's so dark. Okay, so far, the place that would be including all three colors is this weird orangish grayish color down here. And I still have one more to get in here. Y is less than or equal to negative x plus 6. Did I do that right? I did. So I can move this up because I can see that only this part, way down here, is where all four colors overlap. Let's do them one at a time and make sure that that's correct. So there's the green, there's the purple, so now it's in this first quadrant. Then we added this orange color and then the red color. So this is the, I'm going to try to get these to stay. These are the vertices that I need. See them? You can use if you're using Desmos, you can click on those to get the vertices for number 14, that would be 4. We don't need them for number 13. For number 13, you just need to graph this, and then you need to either attach a screenshot or a link over here. I'm going to attach a screenshot so that I can look at it. So you have your own way of doing a screenshot, I'm sure. I don't need the inequalities, so I'm going to leave those off. And I don't need lots of extra stuff. I really only need that triangular, it's not triangle, it's a quadrilateral, but it starts out as a triangle but with the edge cut off. And I'm going to paste that into my worksheet. So I have a nice graph. Now when I do number 14, I'm going to be looking at this region, and the first question says, what are the vertices? Well, you can use the tools in Desmos like I just did to find those vertices, or you can figure them out by your skills in reading a graph. So my vertices are 0, 1, 0, 0, I might have said the same one twice, 2, 4, and 6, 0. Then we are going to maximize this. So we are going to find at which of these vertices would we get the highest amount if we had the function p, like maybe that's for profit, equals 2x plus 5y. So there's 4 rows because we're going to do this for each one. So the first one I'm going to do this for is 0, 0. So I am going to put in 0 for x and 0 for y. So 2 times 0 plus 5 times 0, well 2 times 0 is 0, 5 times 0 is 0, so this is 0. I'm guessing this is not going to be the maximum amount. But now I'm going to redo this for my next vertice was 0, 1. So my function again is p equals 2 times x, but x is 0 again, plus 5 times y. This time y is 1. And then you simplify that. 2 times 0 is 0, plus 5 times 1 is 5. So that's equal to 5. So that's bigger than the last one, so that's so far the maximum. Then we repeat this for 2, 4, and for 6, 0. 2, 4, and we have an extra. All right, so p is equal to 2 times x value, but x is 2, plus 5 times the y value, but y is 4. So that's equal, that's even bigger. We have 2 times 2 is 4, plus 4 times, or 5 times 4 is 20. So that one gives me 24. So far that's the maximum, but you also have to check the last one. And the last vertice is at 6, 0. So p is equal to 2 times 6 plus 5 times the y value of 0. And 2 times 6 is 12, 5 times 0 is 0, so I get 12. So the maximum happened right here. The maximum happened at the point 2, 4, so your maximum value is at the vertex 2, 4. And if you look at the graph, that's that point right there. Might make sense that that is the maximum, but maybe it doesn't. If they had asked me for the minimum, it would be 0, 0, because that one gave me the smallest value. It was just 0. And then you're going to do the same thing for 13. You're going to graph this. And then in 15, you're going to use that graph to write the vertices. And then this time you're going to find the minimum value. So very much the same. All right, then you have some additional problems to do. Numbers 16 and 17, you are to graph the feasible region and then maximize p equals 5x plus 2y. So you're going to repeat the same exact process that we just did, graph this, and then figure out which of the vertices will give you the maximum value. In 17, you only have three boundary lines. And in this one, you're going to find the maximum and the minimum. So there's going to be 2 for this one. And then from number 18, 19, and 20, you only have to pick one of those problems to do. Some of them might take a little bit longer than other ones, depending on, they all do have several parts to do because they're all a linear programming problem, which are real world, so there's going to be some real world constraints to work with. If you want any help with that, please let me know, and I hope you have a great day.